Thank you everyone for coming today. We are the Center for Climate Science and Engineering at the University of Toronto, and we host monthly guest lectures. I am Daniela Boden, the CSE manager, and today we are pleased to feature Dr. Kirsten Ziegfeld. Before we get started, I would like to go through the land acknowledgement. So we wish to acknowledge this land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. Today, this meeting place is still the home to many Indigenous people from across Turtle Island, and we are grateful to have the opportunity to work on this land. If you haven't been here before, we are the Center for Climate Science and Engineering, a research and education center within the Civil and Mineral Engineering Department at the University of Toronto, established in 2019. The CSE is made of 7 faculty members who conform the executive team and who participate together in an interdisciplinary research at the intersection of engineering and climate science. So Oya Merkan is the center director, and she focuses on structural analysis. Marianne Hatzapolo research focuses on transportation. Paul Kushner looks at climate dynamics. Graham Norville at health and safety processes in engineering and chemical engineering. Daniel Posen looks on life cycle assessment. Karen Smith focuses on atmospheric science. Marianne Tucci focuses on building science. And then me, the CSE manager. So why we work together and what we are trying to do. So within some of the key activities going on at the center is education around climate science and engineering. There are 2 graduate courses that have been developed and run in U of T, on top of 8 online learning models that were developed and will be available for use in Ontario higher education environments. The team also works to do research. So the faculty members are carrying out collaborative research project at the intersection of the climate science and engineering. And finally, the team works to do outreach, just like this event, where we invite the public or other university people to come and give a presentation about topics that we feel are aligned with the mandate and vision we have at the center. So our next guest lecturer is Brian Beatty, a senior geothermal engineer and vice president of Salo-Sovereign. He will be speaking about the future of geothermal energy and focuses on the leadership role of U of T in installing geothermal system on its campuses. This event will happen on April 21st at 5 p.m. Keep tuned in the following days for more details about the registration. So now I would like to introduce Dr. Kirsten Ziegfeld, who has come to talk about the science of net zero. She is a distinguished professor of climate science in the geography department at Simon Fraser's University. Her primary research interests are in the long-term effects of human activities on climate. She served as a lead author for the recent released 6th assessment report of the Intergovernmental Panel on Climate Change. She currently serves on the Scientific Steering Committee of the Global Carbon Project. So Dr. Ziegfeld, we welcome you, and the floor is yours.
Thank you very much, Daniela. Thank you so much for the invitation. It is a pleasure to be here. So maybe if you could stop sharing your slides, then I can start sharing mine. Okay, good. So is this visible? Yeah.
Yes.
Okay.
We can see your slides.
Okay, good. So as Daniela already said, I am going to talk about the science of net zero. So I will talk about the scientific foundations of this net zero concept, and will also offer some reflections about its utilities, but also about some of the risks that this concept entails. So the first question really is what is net zero? So net zero refers to net zero carbon dioxide or greenhouse gas emissions. And there's this little word in here, which is net, which actually, as we will see later, complicates things quite a bit. So net zero means that residual emissions of greenhouse gases are balanced by anthropogenic greenhouse gas removals. And this concept of net zero has gained traction in the wake of the Paris Agreement, which called on nations to limit warming to well below 2 degrees Celsius above pre-industrial levels and to pursue efforts to limit warming to 1.5 degrees. And in the report that was published in 2018 by the UN's Intergovernmental Panel on Climate Change, it was clarified that limiting warming to 1.5 degrees requires reduction in carbon dioxide emissions by about half that by 2030 and reaching net zero CO2 emissions by 2050. And since then, many entities, so these include countries, these include institutions and companies, have set target in terms of net zero emissions. And currently about 88% of carbon dioxide emissions are covered by net zero targets. So what I'm going to do here, I will first talk about carbon in the climate system and understand its role in setting concentrations of carbon dioxide and temperature. And then I'll talk briefly about the physical climate response to show why it is actually necessary to limit or to reach net zero carbon dioxide emissions in order to limit warming to a specific level. So you've probably seen this curve here many times. So this is the famous Keeling curve, which shows the change in the atmospheric CO2 concentration as a function of time. So when they started measuring in 1958, carbon dioxide levels were below 320. And now we're actually here scratching the 420 ppm level. So in fact, in average over the month of February, global carbon dioxide concentrations were at 419 parts per million. And it is well known that this increase in concentrations of carbon dioxide in the atmosphere is driven by anthropogenic emissions. So these include carbon emissions from fossil fuel burning, but also carbon emissions from land use change due to activities such as deforestation. And yeah, here in the fossil fuel emission curve, so this slight dip here in 2020, this is due to the COVID pandemic, but as analysis have shown, the emission level in 2021 has actually rebounded to the 2019 level. So how does the carbon cycle respond and the climate system respond as we put carbon emissions into the atmosphere? So this slide here shows the main stores of carbon dioxide. These are mainly the ocean, followed by the land and the atmosphere. And these stores here are given in billion metric tons of carbon dioxide. And naturally, these carbon stores exchange large amounts of carbon, which are indicated by these orange arrows here. So the atmosphere and the land, they exchange around 500 billion metric tons of carbon dioxide per year, and the ocean close to 300. So fossil fuel emissions and land use emissions or averaged over the period between 2011 and 2020 were in the order of 40 billion metric tons of carbon dioxide per year. And about half of those remained in the atmosphere, and the other half was taken up by sinks on land and in the ocean. So currently, or over the past decade, about 50% of the emissions that we release into the atmosphere have been taken up by these natural land and ocean sinks. However, something to take into account is that the efficiency of these sinks is expected to decrease with further carbon emissions and further warming. And this is illustrated here with a figure that is taken from the most recent IPCC Working Group 1 report. So here, these boxes at the top, they show emissions of carbon dioxide into the atmosphere. So again, given in billion metric tons of CO2. And then these colored boxes, this is the amount of those emissions that are taken up by the ocean and the land. And as you can see, the amount increases with the amount of emissions. So here, these are different scenarios, so different possible future evolutions of our socioeconomic system, ranging from scenarios with very ambitious climate mitigation to business as usual scenarios. So the amount of emissions put into the atmosphere increases from left to the right. And as is evident from this figure, as the amount of emission increases, also the amount taken up by the ocean and the land increases. However, the fraction or the percentage of emission that is taken up decreases with the amount of emissions. So the numbers decrease as you go from left to right. So within these donut chart here. So this means that as we put more carbon dioxide into the atmosphere and as the climate warms, the efficiency of these sinks decreases. And here in this relatively high emission scenario, the amount that would be taken up by the ocean and the land now is reduced to 38% from the current number of 50%. And this is due largely to what we call climate carbon cycle feedbacks. So effects of climate change on these natural sinks, which then reduces the ability of these sinks to take up carbon. So due to these feedbacks and to processes within the carbon cycle, the carbon that we release into the atmosphere pretty much from a human perspective stays there forever. And this is illustrated in this figure here. So on the vertical axis, this is the percentage of carbon dioxide emissions that remain in the atmosphere as a function of time. And here, the first part of this figure here, this is zoomed into 500 years, but then the time axis extends 10,000 years into the future. And then these different colors, these are lines that correspond to different amounts of carbon emissions put into the atmosphere. And here the unit is petagrams, which is the standard unit used in carbon cycle science. But luckily, this corresponds to billion metric tons of carbon in this case, not carbon dioxide. But the main point here is, so these lines here at the top, these are lines with larger emissions, and then the amount of emissions put into the atmosphere decreases as we move down. And the main point here is that after 500 years, 30 to 70% of the atmospheric carbon dioxide emissions is still in the atmosphere. So a very large fraction still is in the atmosphere many hundred years after they were released. And if we emit a lot, then actually a large percentage remains in the atmosphere. So this is a very important finding to understand the relationship between carbon emissions and temperature. So carbon dioxide, once in the atmosphere, is very difficult to get out. So now let's talk about the physical climate system response to carbon dioxide removal. So this here is a cartoon of the greenhouse effect, which I assume you are all familiar with. What I would like to point out here is that the enhanced greenhouse effect, or the greenhouse effect that is enhanced by human emissions of greenhouse gases, creates an energy balance at the top of the atmosphere. Energy imbalance means that more energy remains within the system than actually leaves the system. And the Earth restores energy balance by warming. And the reason is that as the surface or the temperature of the Earth warms, more radiation is emitted to space. And if, let's say, there were no ocean in the climate system, then this energy balance would be restored quite quickly. However, we do have inertia in the climate system, which is largely related to the ocean, which slows and delays warming, first due to the high specific heat of seawater, and then secondly, due to the ability of the ocean to mix heat into deeper layers of the ocean. So if we apply an energy imbalance at the top of the atmosphere, then it takes the ocean a long time to adjust to that energy imbalance. And this is what we call ocean thermal inertia. And to illustrate this, I pulled a figure here from a paper by Matthews et al. From 2008, which shows the change in ocean temperature over a time frame of 500 years. And so if we look at this solid blue line here, oops, sorry about that. So this is for carbon emissions that stop in 2100. Okay, so in 2100, even though we stop releasing carbon dioxide into the atmosphere, you see that the ocean still continues to warm and will do so for several hundred years, even after 2500. So the ocean, it takes the ocean several hundred years to adjust to this energy imbalance, which introduces inertia into the system. And so the longevity of carbon dioxide in the atmosphere and this ocean thermal inertia, they're really at the core of what we need to understand why stabilizing temperature requires reaching zero carbon dioxide emissions. And I'll illustrate this again here. So, there are many papers that have shown this. I took the ones that I show here are from a paper of Gillett et al. 2011. So these here to the left, these are cumulative emissions. So cumulative means that they're added up year by year. Okay, so it is, perhaps we could also say total emissions. So the total amount of emissions that is released up to a given year. And when these lines plateau, it means that emissions are zero. So in this green case here, emissions increase according to the historical, to the observed emissions, and then are held constant shortly after the year 2000, whereas in this red case here, carbon dioxide emissions continue to increase according to business as usual trajectory until the year 2100, and then they are set to zero. Okay, so in this green line, emissions are set to zero or are stopped around the year 2000, and in this red case, around the year 2100. So then let's look at the concentration of carbon dioxide in the atmosphere. So even though we stop emissions, so if we look at this red curve here, the concentration in the atmosphere remains high for a very long time. So here the time scale is 1,000 years. So there's a somewhat rapid decline at the beginning, which is due mostly to carbon uptake by the terrestrial biosphere, but then the uptake slows down. And by the year 3000, still again, close to 60 to 70% of the carbon dioxide emitted into the atmosphere is still in the atmosphere. So here at the bottom, this shows the ocean warming. So here the label says thermospheric sea level anomaly. What this means is the expansion of the ocean due to warming. But this is basically an indicator for the warming of the ocean. So what we see is, again, for this red trajectory, so even though we stop emitting in 2100, the ocean continues to warm for 900 years and probably even longer. And so these two responses here, so the declining carbon dioxide concentration and then this ocean thermal inertia, they balance out. And the idea here is that some of the same ocean processes are associated with carbon and ocean heat uptake. And what they give is an approximately stable surface air temperature. Okay, and again, the reason is that this decline in the atmospheric CO2 concentration following zeroing carbon dioxide emissions is compensated by this continuing warming due to ocean thermal inertia. And so these two effects more or less compensate and give us a stable temperature. So the corollary here then is that in order to limit warming or to halt warming, we need to reach zero carbon dioxide emissions. So this is I would say the first key point. So now research over the past decade has shown that global warming is proportional to cumulative carbon dioxide emissions. And this is illustrated very nicely in this figure here, which is also taken from the latest IPCC Working Group 1 report. And so here on the vertical axis, this is global surface temperature relative to pre-industrial, global surface temperature change relative to pre-industrial as a function of cumulative, or again, total carbon dioxide emissions, again, given here in units of billion metric tons CO2. And we see that both historically, which is this wiggly black line here, but also in future scenarios, this relationship between warming and the total amount of emissions is linear. What this means is that a given level of carbon dioxide emissions that we put into the atmosphere has a well-defined amount of warming. And the slope of this line is somewhat uncertain because it is related, and this is indicated also by these envelopes here, because of uncertainties and climate sensitivity, which is how much the climate system warms in response to CO2, but also uncertainty in carbon cycle processes. Okay, so warming is proportional to cumulative carbon dioxide emissions. And what this also means that, so again, if we turn this around, if we want to limit warming to a specific level, so let's say 1.5 degrees, then there's a well-defined amount of carbon dioxide that we need to limit our emission to. And this finite amount of carbon dioxide, this is what is called a carbon budget. So again, a carbon budget is a finite, so this is very important. Finite here really means over all times. So it's something that doesn't renew. So a finite amount of carbon dioxide that can be released into the atmosphere while keeping global warming below a given limit. And to illustrate this, I pulled this visualization from the Global Carbon Project. And here the idea is to illustrate the budget as a bucket. And as emissions are released into the atmosphere, the bucket gradually warms until it fills. So what the filling of the bucket is a metaphor here for the carbon budget being exhausted. So this year, this is a function of time. So we're now in the early 1900s, and it also distinguishes between different regions of the world. And the simulation here goes to the year 2019. So this is now almost 3 years ago. And at that point in time, only 9% of the carbon budget that is consistent with limiting warming to 1.5 degrees was left. So just to give you an idea of how large this budget is, so these numbers are again from the latest IPCC Working Group 1 report, and they gave these remaining carbon budgets. So remaining means as of a specific date, and here the date is taken to be the beginning of the year 2020. And the numbers that I'm showing here, they are consistent with limiting warming to 1.5 degrees, but the report also gives you numbers for 1.5, 1.7, and 2 degrees, and I think even higher. So I did mention the uncertainty that is related to uncertainty in climate sensitivity and carbon cycle processes, and for this reason, carbon budgets come with a likelihood. So they come with the chance, or with the likelihood of actually staying within the given temperature limit. So if we as a society are comfortable with the 50-50 chance of staying within 1.5 degrees, then the remaining carbon budget is 500 billion metric tons of CO2. And to put this into context, remember we said earlier that we're currently emitting 40 billion metric tons of CO2 per year into the atmosphere. And so this would be at current emission rates, this would be 12 years. If, on the other hand, we want a bit more certainty of limiting warming to 1.5 degrees, then we could go with the 2 in a 3 chance, and then the carbon budget would be reduced to 400 billion metric tons of CO2, which is equivalent to about 10 years of current emissions. But I should also point out, this is from the start of 2020, and we've continued to emit about these amount of emissions. If we're interested in the remaining carbon budget as of the beginning of 2022, then we would have to subtract around 80 gigatons, leaving us with 10 years for the 1.5 chance and about 8 years for the 2 in a 3 chance. So the key points that I wanted to make so far is that warming that is induced by carbon dioxide halts when CO2 emissions reach net zero. And this is really a geophysical constraint. And that the level of warming that we achieve or that we reach by the time net zero CO2 emissions are reached will be determined by the total amount of net CO2 emissions emitted up to that point. So now let's unpack this idea of net zero a little bit more. So according to the definition of the IPCC, net zero CO2 emissions is defined as a condition in which anthropogenic carbon dioxide emissions are balanced by anthropogenic carbon dioxide removals. And here, anthropogenic means that these removals are deliberate. So they are different from these natural removals of the land and the oceans that I talked about earlier. So these would be referred to as natural removals. So anthropogenic removals are deliberate CO2 removals through human activities. And I'll show a few examples of those in a moment. So in this definition here, this there is an implicit assumption, which is that achieving balance assumes that the climate effect of a CO2 emission is equal and opposite to the climate effect of a CO2 removal. Right, again, in the context of the Paris Agreement, we're talking about net zero with the goal of limiting warming to a specific level. So what we're assuming by allowing to trade between emissions and removals is that, let's say, 1 unit CO2 emission has an equal and opposite effect to 1 unit CO2 removal. However, as I will argue in a moment, this is not necessarily the case. So first of all, what are some potential carbon dioxide removal methods? And there are, I would say, usually they are categorized in different categories. So depending on either the sequestration or the storage mechanism. Here I refer to them as perhaps more technological and engineered methods. And one of them is direct air capture of carbon dioxide from the atmosphere, which probably many of you at the center are already familiar with. So here the idea is that air is sucked in to these devices, and then there's the chemical process that strips the carbon dioxide out of the ambient air, and this carbon dioxide is then either disposed underground or made into products that can be used for different purposes. And so here the idea is we're taking carbon dioxide out of the atmosphere, and then through capture infrastructure, we place the carbon into the geologic reservoir. So then another category of these carbon dioxide removal methods includes what are referred to as nature-based climate solutions. So these are solutions that use ecosystems, both on land and in the ocean, which naturally sequester and store carbon to actually sequester and store even more carbon than they would naturally. And I think the most prominent of these nature-based climate solutions is reforestation. So planting trees in areas where that were previously deforested, or afforestation, which means planting trees in area where there previously was no forest. And here the idea is that through processes of photosynthesis, carbon dioxide is taken out of the atmosphere and then stored in carbon stores on land, or if we talk about marine ecosystems such as coastal ecosystems, for example, then in the coastal ocean. And so if we think especially about these land-based methods, right? On one hand, they sequester carbon dioxide from the atmosphere, but then, as is illustrated in this figure here, they also affect the land surface. So if we plant trees in an area that had grasses or maybe agricultural crops beforehand, then planting trees changes the turbulence at the land surface, which then has an effect on latent and sensible heat fluxes, so the exchange of heat between the surface and the atmosphere. Also, often trees are darker than grasses or agricultural surfaces, so they reflect less incoming solar radiation, and this is a property that we call albedo. So the albedo of forested areas is usually reduced compared to a non-forested area. And all this is to say that in addition to the effect of these removal methods on carbon dioxide, these methods often have other effects on the Earth system, right? Through their modification of the surface energy balance, for example, as is in the case here of afforestation and reforestation. And so this is why, assuming that the climate effects of emissions and removals is actually equivalent, is not necessarily justified. So here I already mentioned these, so we call them biophysical effects. So this is our effects of vegetation on fluxes of heat, for example, but also water vapor, and on radiation. And one example of a biophysical effect is the change in albedo, but also changes in evapotranspiration, for example. And especially in the case of forests, and even more so if we plant forests in regions of seasonal snow cover, then actually these effects can have a net warming effect that counters the effect of carbon dioxide removal. And in effect, so this is very relevant for Canada, in high latitude regions, the albedo effect actually dominates. So from a climate perspective, it is actually, it results in net warming if you do plant trees for carbon sequestration. Also, some other carbon dioxide removal methods, they can result in release of other greenhouse gases. So for example, peatland restoration can result in release of methane, which is a very powerful greenhouse gas. And some other methods that have to do with storing carbon in soils through changes in agricultural practices. For example, they may release nitrous oxide, which is also a greenhouse gas. So while these efforts may be successful at removing carbon dioxide from the atmosphere, again, they may have unintended consequences, climate consequences, in the form of release of other greenhouse gases. Also, carbon stored by CDR, and this is true for many land-based carbon dioxide removal methods, the carbon that is stored can be vulnerable to natural disturbances. So things like wildfires or insect outbreaks, and also to human disturbances. So let's say if we decide to plant a forest in a given area, there's no guarantee that actually that forest may remain there forever, because there may be land use change decisions that are made that interfere with that carbon storage. And then finally, so this is something we published last summer. The carbon cycle and climate response to carbon dioxide emissions and removals is asymmetric. So what this means is that, so not taking any of these earlier effects into account, just because of non-linear effects in the carbon cycle, an emission of carbon dioxide released into the atmosphere is more effective at raising atmospheric CO2 than removal of CO2 is at lowering it. So this means that there's an asymmetry in the emissions, in the effect of emissions and removals on the atmospheric CO2 concentration. And so if you're offsetting an emission with the removal, you may actually end up with the higher CO2 concentration level than if you were to avoid that emission in the first place. Okay, so these are all reasons, and these, so there is on the biophysical effect of afforestation, there's quite a bit of research out there, but many of these effects here are only starting to be understood. I think we know quite a bit about forests, but many of these other or the climate effects of many other CDR methods, and also the more general biogeochemical effects of these methods is still poorly quantified. So I wanted to show an example here of for example, how offsetting a carbon dioxide emission with a non-permanent carbon dioxide removal can actually result in additional warming. And so here on the left-hand side, these are atmospheric carbon dioxide concentration, and the blue line. Oops, I just realized that these arrows have shifted here. So disregard those, please. So the blue line here, which lies under the yellow one. So this is our baseline. So this is a relatively ambitious emission mitigation scenario. So in this IPCC family group, scenario family group, it's the SSP1 1.9. which is more or less consistent with limiting warming to 1.5 degrees. So now, if in addition to these aggressive mitigation, we also deploy, let's say, a land-based CDR method that sequesters CO2, but then is affected by some kind of disturbance. So for example, think of a forest that is planted and then is burned down. Then this would be this red trajectory called temporary removal. And so what it does, in this phase of carbon storage, it shaves the peak off of the CO2 concentration and off of temperature, but then returns to the baseline scenario. So temporary carbon storage can actually have a benefit if it is additional, right? So in this case, we are deploying the CDR in addition to ambitious emission reductions. However, if we use it as an offset, as is the case in this yellow line here, so now the assumption is we use CDR to offset fossil fuel emissions. So it could be from from natural gas or from oil. And so because we use it as an offset during the time that the CO2 is sequestered, the trajectory is the same as for our reference scenario, because we use that to offset additional emissions. And then shortly after 2050, when the carbon dioxide is released back into the atmosphere, so again, this could be due to a forest fire, then you see that now this yellow line in terms of carbon dioxide concentration, but also in terms of temperature, lies above the baseline. So what this indicates that if we use this carbon storage that turned out to be temporary to offset fossil fuel emissions, then in the long term, we do actually end up with more warming. Okay, so I think, I'm at the end of my presentation and also of my time. So let me briefly summarize and conclude here. So reaching net zero carbon dioxide emissions is a geophysical requirement for halting warming. And the level of warming that we will reach at the time net zero CO2 emissions are reached will be determined by the total amount of carbon dioxide emissions emitted into the atmosphere up to that point. So then what I showed here is that the climate effects of carbon dioxide emissions and removals are not always equal and opposite to each other. So in a sense, they're not equivalent because of these these several effects that I just mentioned. And because of that, if we're pursuing net zero by balancing CO2 emissions with CO2 removal, we could actually end up with more warming than we would if we were to avoid those CO2 emissions in the first place. And so I think this has many implications, but I would say the sort of a high level implication is that policy frameworks that regulate more generally these net zero CO2 emissions, and more specifically things like carbon offset protocols, they need to take this non-equivalence of CO2 emissions and removal into account, because otherwise net zero may result in additional warming. So I will stop here, and I'm happy to answer any questions. Thank you.